Ladies and gentlemen, welcome to this expert workshop on flexibility provision from biogenic gases, an expert workshop from task 44 of IEA Bioenergy. My name is Jaap Kiel. I'm a program and business developer at TNO in the Netherlands, focusing on bio-based options. And I'm also the Dutch representative in task 44. And today I will try to moderate this session. And first, perhaps good to start with some organizational things. It is scheduled that this session will last about 2.5 hours. So we try to stick to that time schedule. And we'd like to have considerable interaction with you as participants. Of course, that's always an issue with these workshops, but we've provided 2 facilities for that. One is we would like to ask you to use the Q&A option in this Zoom webinar to ask questions, and they will be addressed in one way or another. And the other way of getting interaction with you is that during the workshop, we will ask 2 Slido questions to ask your input on the questions provided. As said, this workshop is on flexibility provision from biogenic gases. In general, biomass has many utilization options. That makes it, let's say, complex, but also it provides many opportunities to use biomass in both the energy and the materials system. And in addition, biomass and bio-based options provide a lot of flexibility. And in the future energy systems, this flexibility is a valuable asset. And therefore, we think that bio-based options will be an important element in these future both energy and materials systems. That is the reason that within IEA Bioenergy, there is a specific task on flexibility and system integration. Today, we hope to shed some light on what are the flexibility options, and with a specific focus on biogenic gases, so gaseous bio-based options. I think we have an interesting program with, after a short introduction, some keynotes from industry to show the industry perspective, both from an energy provider's perspective, but also from a perspective of an industrial technology provider. And then we will provide, let's say, an overall structure, trying to categorize the different flexibility options, and after that dive into the specific technology options, in particular for gasification-based systems as well as biogas-based systems, and then conclude with a discussion and a summary. So with that, I would like to introduce the first speaker. And the first speaker is Elina Maki. She is from VTT in Finland, where she is a senior scientist. And she is the task lead of task 44 on flexible bioenergy and systems integration. And she will provide an introduction to flexible bioenergy. Elina, the floor is yours.
Thanks a lot, Jaap, and hello also from my side, and welcome. Can you see the presentation?
Yes.
Yes.
Yes, great. So I will try to provide you a very short introduction on how Task 44 sees flexible bioenergy. I will try to keep it short to give more room to our technical experts. As Jaap mentioned, the topic is very timely as we are nowadays discussing more and more about energy security, how to substitute natural gas with biomethane, and also about resource sufficiency. in our current geopolitical situation in Europe. And on the other hand, we have increasing amounts of variable renewable generation in the system, which is good, but also requires flexible resources. And at Task 44, we think that biogenic gases can support these issues. A bit more about Task 44, flexible bioenergy and system integration. Our key objective is to provide a clearer picture how flexible bioenergy can support the energy system in multiple ways. And to do this, we cover different aspects or topics from the field. We cover technical aspects, how to integrate flexible bioenergy in the system, how we could accelerate the implementation, and also how flexible bioenergy connects to other value chains, especially green hydrogen and bioenergy with carbon capture and storage or utilization-based value chains. We have globally 8 members, and of course we welcome always new members to join our work and task. And you can find more information and get in contact with us through our website and our LinkedIn group. Then how we see the role of bioenergy in the bigger picture in the energy system. First of all, we need sustainable resources and modern bioenergy. It should come increasingly from residues and waste resources. And we should be able to use different feedstocks according to their availability. And here we can talk about feedstock flexibility. Then, as mentioned, we have more and more fluctuating renewable power in the system, and it requires a flexible counterpart. And here we can talk about operational flexibility. It refers mainly to the power sector, but also to other sectors through sector coupling. Then we also have, or we can produce durable biofuels, especially for hard to abate sectors like maritime and aviation, but also we can produce, for example, biochemicals. Then we have increasing amounts of clean hydrogen in the system. And here the interesting question is how clean hydrogen and bio-based value chains can interact, and where we can find the most feasible synergies between these value chains. Hydrogen can connect to bioenergy, first of all, in a way that we can produce hydrogen from biomass. But on the other hand, we also can use hydrogen in many bio-based processes to, for example, upgrade biofuels or boost the yield. Then last but not least, we have in the picture CO2, which we can capture from many bio-based processes and bioenergy production, and together with hydrogen use again for fuels production. It must be noted that this picture can look very different in different countries because in different countries we have different energy systems, different market mechanisms, different biomass availabilities, and also different climate strategies. So the picture varies between countries. And as you can see from this picture, bioenergy can provide different services to the system. And when screening different technical options at Task 44 to provide flexibility from biomass, we ended up to 3 different categories. First of all, we have short-term flexibility services from bioenergy. And under this, we have first backup or peak generation, when bioenergy can substitute or complement renewable energy production from variable resources when there is not enough of those available during a given time. Then on the other hand, we also have times when there is too much production renewable energy production available compared to consumption, and then bioenergy can step in with negative ancillary services. So bioenergy can actually uptake electricity when there is more available than needed. Then flexible bioenergy goes way beyond short and mid-term flexibility services, and we also have long-term flexibility services from bioenergy. And this basically means biomass-based energy carriers, which can be stored even seasonally and transported within the existing infrastructure. And from these categories, we can see that bioenergy allows us to shift resources in time and in space, but also between different sectors according to market demand. And with all this information, I will end up with the definition for flexible bioenergy from task 44. So we have defined flexible bioenergy as a bioenergy system that can provide multiple services and benefits to the energy system under varying operating conditions and or loads. And some examples of this include technologies that can support variable renewable energy in the system, like wind and solar energy, dispatchable production of energy and other products according to market demand, pollute generation systems producing multiple products, long-term storage options, and finally ancillary services to support system reliability. And I must note that this definition is evolving over time when we gain more information and insights on the topic. But this is how we define the flexible bioenergy at the moment. And with this, I will hand over back to Jaap, and looking forward to the discussion and presentations, as it's very important to bring together the systemic view and the end user perspectives with the technical solutions. Thank you.
Thank you very much, Elina, for your introduction. There was a question on the chat whether the presentations will be made available, and indeed that will be the case on the IEA Bioenergy website. Once again, I would like to request all participants to use the Q&A and not the chat. It's more handy for us to deal with the questions in the Q&A. Well, following this introduction of Elina, we would like to ask you the first Slido question. So Marco, can you put that on the screen? There it is. So the question is, what do you see as major possibilities for flexible bioenergy? So we would like to get an impression of, let's say, the ideas with which you came to this workshop. So please answer this question. Multiple answers are possible because probably you already, that would be the first thought, that it's not a one-dimensional thing. So where do you see major possibilities for flexible bioenergy? I don't know, Marco, how long it will take that you can show the first results.
Now we are on half of the participants, so waiting a few seconds.
Yeah. Okay, so here, sorry, yeah, I see the results. Quite a scattered view, you can say. And I think that is basically in line with, well, the first introduction of Elina, where she already indicated that there are many flexibility options. there is no clear winner, I would say, if you look at these results. Well, perhaps also a question to the speakers coming up, whether they can, they share this opinion, let's say common opinion of the participants, that indeed there are many flexibility options and that there is no one really standing out amongst them, or whether they see that they do see a clear winner, and perhaps that's also time dependent. With that, I would like to go over to the three industry keynotes we have in this workshop, starting with the first one, which will be given by Tuka Hartika from Helen. He's the business lead for renewable hydrogen and power to X at Helen in Finland. And he will give a presentation on sector coupling and flexibility. Tuka, the floor is yours.
Thank you, Jaap. I will share my presentation. I hope you can see it in presentation mode now. Yeah. Okay, so thanks for the introduction. My name is Tuka Hartika and I'm working as the business lead for renewable hydrogen power to X here at Helen. I'll give a brief update on things that we're doing at Helen and how do we see the flexibility and sector coupling in general. But first, very briefly about Helen, because it might be that not so many people know the company since we are a local Finnish energy provider. But we've been already in place for more than 100 years. So originally we were founded to provide electricity and heat for the city of Helsinki. And ever since we've been working hard on providing very reliable heat and electricity in Finland, in Helsinki, and in many other cities as well. And we have an ambitious target to be carbon neutral by 2030, which is quite a challenge, but I'm very confident that we will make that. So we are a company of approximately 1,000 employees and 1.3 billion euro turnover last year. We have 1,400 kilometers of district heating network here in Helsinki and 6,200 kilometers of electricity networks. Our main business areas today are solar and wind, electricity network and sales to B2B and B2C customers, electric vehicle charging operations, heat and cooling, hydrogen and power to X, and then smart buildings. But if we go to the topic of today, so here's a illustrated picture of how we see that a carbon neutral world could operate. So it is very interconnected, and we need many different sectors to be coupled together. And the main starting point would be fossil-free electricity or energy in general. So we need electricity from solar and wind, hydro, nuclear, and also from biogas. There we have a good starting point, but we do need to form this electricity into something more usable for the society when we need, for example, fuels or food or polymers or chemicals. So we need another piece to the puzzle. So first of all, we need hydrogen, and then we also need CO2. And biogenic CO2 is something that we can use to create even negative emissions, so remove carbon from air in certain cases. If we use an electrolyzer to produce hydrogen, we always produce heat as well. So roughly 1/3 of the electricity that we put into the system comes out as heat. And this heat could be utilized in district heating networks. If you have a low temperature district heating network, you could even use the heat as such without a heat pump, or if you need to boost it up, you can have a smaller heat pump to boost up the temperature. But then you have one piece of the puzzle. So you have the hydrogen, and then you need the CO2, which you would capture from a biomass plant. And with these two building blocks, you have a basically option to produce almost anything you need. And we see that especially hard to abate sectors like aviation and marine are very important sectors to have synthetic fuels for. We could also produce food from these ingredients, so protein. There's an extremely interesting startup in Finland called Solar Foods that can produce protein called solein from CO2 and hydrogen. And then, of course, you have the chemical industry that you can also apply with these pieces of the puzzle. And this all could happen within one country as well. So you don't need such a long supply chains as you need today. But what you need is flexibility and sector coupling. And I will now present one example of how we see the topic and a couple of the challenges in this sphere as well. So first of all, what we need to produce the hydrogen with electrolysis, you of course need electricity, a lot of it. If we take here an example that we have a hydrogen production unit, 100 megawatt alkaline electrolyzer, and you would like to run it basically, let's say 8,000 hours per year, because typically the hydrogen users need quite a continuous flow of hydrogen. So what you would need is you would need to get 280 megawatts of wind power for this system. So in Finland, the capacity factor is about 35%. So to cover the whole energy need, you need 2.8 times the power that the electrolyzer requires. What you would also produce then is 30 megawatt hours of heat every hour, which is quite usable in a district heating network. And why I mention here that only 65% of the hydrogen is green is because of EU legislation, where you would most likely need to match the wind or solar energy with the hydrogen production hour by hour. And now you need to basically oversize your wind assets as well on certain times, and then you basically have to sell the excess power to the grid, and you won't be able to get 100% green hydrogen according to these rules. And small buffer storage is often needed to balance out the fluctuations. And with this kind of option, this is actually quite a cost-efficient way. I've used here an example of the Finnish electricity prices in a couple of years back before the special situation. So you could produce hydrogen with 3 euros per kilo as a baseload model. And as you can see in the price distribution, electricity covers about 3/4 of the costs, and 27% would come from the electrolyzer capex costs. Okay, we take another perspective where we actually would like to increase the green hydrogen amount. So we fully oversize the wind asset. So we take 400 megawatts of wind power to just have more green hydrogen. In this case, we can achieve also 2 tons per hour baseload hydrogen production, but we also increase the costs, because what happens is that you have to sell more wind power to the grid, and typically this then cannibalizes the value that you get from the wind asset, and there's too much wind in the system, and therefore you don't get as good price for your wind assets as you would in the previous case. So in this kind of option, the average price of hydrogen would be roughly 3.5 euros per kilo. And then if we take the third option, where we would like to get 100% green hydrogen, so basically producing hydrogen all the time, we would have to get roughly 550 megawatt of wind power supply and oversize the electrolyzer. So the electrolyzer would be almost doubled in this case, but it would only run half of the time. Then also we would need hydrogen storage for 11 days to cover those non-windy periods in the summertime. And this would add to the cost tremendously. With this option, we can provide 2 tons per hour of hydrogen, but the cost would go up to 6.7 euros a kilo. And here you can see as well that the capex cost is now the one that actually influences the most on this total cost of the hydrogen, and electricity is much smaller price. So what this basically means to show is that that we need balancing power as well. We need something else together to combine with wind and solar to balance the grid, and that will be very cost efficient. And also the regulation shouldn't discriminate these non-fossil sources of electricity, which you could use for producing hydrogen as well. Okay, that was my example, and then I just briefly want to advertise our project that we are now developing. So this is called 3H2, so Helsinki Hydrogen Hub, and we are now developing this project in Helsinki. So we have a small solar park connected to an electrolyzer. The electrolyzer will also be connected to the grid. Then the produced hydrogen will be stored in a low pressure storage. And the hydrogen main use will be going to heavy duty traffic. So there will be a hydrogen refueling station as well. But because we want to increase the flexibility, so we also have a small terminal to import and export hydrogen, and also a fuel cell to provide grid balancing services when that makes the most value. And all the heat that's produced in this system from the electrolyzer and from the fuel cells and from compressing will be then utilized in a district heating network with a heat pump. And by this, we can increase the total energy efficiency to about 90%. So it will significantly improve the business case and also the efficiency of the system to just utilize all the waste. And we hope that this system that we're now building will be up and running by 2024. And one of the main things is to develop also the optimizing system for this whole solution. So the digital solution for this to operate it in an optimal way. But thank you. That was briefly what I wanted to present to you today.
Thank you very much, Tuukka. I think you clearly showed that providing flexibility for providing flexibility, bio-based options are not the only option. There is an important role for hydrogen as well. How do you see this? Let's say, what share of bio-based options could you envisage? Let's say in the Finnish situation.
Well, I think it's a hard discussion always because the role of bioenergy is very much debated. What is sustainable and what is not. So I don't see that the share of bioenergy would be increasing very much. Finland is using quite a lot of bioenergy already, but I think utilizing carbon capture would bring a new element to the story, and I think that definitely should be done. And there is sustainable ways of using bioenergy. I fully agree. So I see bioenergy as an important part of the puzzle. But there is definitely no silver bullet, so we need all these options.
Okay, thank you very much. I see no pressing questions in the Q&A. So thank you very much, Tuukka. And we go over to the second industry perspective, which will be given by Teresa Schubert. She is a senior expert research and deputy department manager of research and energy technology department at Bioenergy in Austria. She will provide, let's say, the perspective, the Austrian perspective, or in particular the perspective from Bioenergy. So her presentation is entitled Bioenergy's vision of a sustainable energy and resource supply for Vienna. Teresa, the floor is yours.
Thank you very much. I hope you can hear me and see my presentation now.
Yes.
Perfect. Wonderful. Thank you, and welcome from my side as well. Thank you for the nice introduction. I would like to show you what Bioenergy, the energy supplier of the city of Vienna, envisions for a sustainable energy and resource future. And firstly, I would like to start, with a short introduction. How does the actual situation in Austria and Vienna regarding the energy consumption and the sources of energy is, to understand why we are interested in biogenic gases for flexibilization and what the role of Bioenergy is in this system. I would like to introduce to you furthermore a decarb study we did, how the future of a climate neutral energy system of the city can look like. So we're a bit less ambitious than Helsinki, so we aim for 2040 compared to 2030. And I would like to finish with the topic of gasification, because it's one of the pathways we see great potential in to generate these biogenic gases, especially in the urban area. And I would like to introduce to you our research project in this context. So let's start with our energy consumption. Vienna is, in comparison to Austria, quite efficient in the energy consumption. So we need per inhabitant about half of the energy compared to Austria overall. But if you have a look in detail in the energy demand, our share of natural gas in orange, as you can see, is much larger compared to Austria in general. In the urban area, we don't have that many renewable energy sources compared to the more rural areas, and especially in heating, but also in electricity generation, we're quite dependent on natural gas. And as you might notice, the last months were quite troublesome in regard of gas utilization. So that's quite a pressing topic. So in Vienna, what do we need this gas for? There are mainly two different applications. Here you can see the gas demand of Vienna. So it's about 20 terawatt hours per year, where one share goes directly into usage in households, in heatings, in boilers, in flats and houses, but also in companies to produce process heat. But the larger share, about nearly 12 terawatt hours, is converted mainly by combined heat and power plants into electricity and district heating. And that's why we, as Bioenergy, as energy provider, discuss a lot about gas and the actual situation and how the future could look like, because that's our role, this conversion process. So who is Bioenergy? Bioenergy is Austria's largest energy supplier. We supply energy for about 2 million people in the form of power, gas, heating and cooling. In the future, maybe other energy carriers as well. We have about 2,200 employees, and we invest largely to increase this renewable electricity share within the city, but also outside the borders of the city. So we operate, for example, large wind farms and PV plants and hydropower plants outside of Vienna, because of the rural area, which is quite easily to generate renewable electricity compared to the urban area of Vienna. And we provide also heat for about 440,000 households within the city. So the district heating in Vienna is quite large, and we provide this partly by converting about 1 million tons of waste. So Bioenergy, besides converting energy in the form of gas, for example, also operates 4 waste incineration plants at the moment to generate district heating. Keep that in mind because it will be important afterwards. So as you can see, we invest largely in the renewable electricity part, but we have to think about how the energy system will look like in the future. On the next slide, I'm sorry. So on the next slide, you can see how we provide this energy. So in regard of power of electricity, a large share comes from thermal generation. We have a biomass plant, but we also operate gas plants, combined heat and power plants. And as you can see, our renewable share is still increasing, especially in photovoltaics and wind power. And on the heat production side, we have mainly 3 main contributions: the cogeneration, so the combined heat and power plants, and our waste incineration plants and waste heat sources from different sources. As you can see, on the power side and on the heat side, at the moment, we depend a lot on natural gas. Natural gas, which is mainly imported. In Austria, about 10% of our energy or of our gas is produced inland, 90% are imported. And furthermore, natural gas is not climate neutral. It's not CO2 neutral. And as I've already mentioned, the city of Vienna is our owner of the company of Bioenergy and has the aim of being climate neutral by 2030. So to achieve this goal, we had to think about how this system could look like. Starting from 2019, from a status quo, where large amounts of the energy comes from fossil sources. We built scenarios how this future could look like based on some assumptions given by politics or the system itself. For example, that electricity will be fueling mobility in a major part, especially the public transport, but also individual transportation. And the heating and cooling will be provided on the one hand by electricity, by heat pumps, and by district heating. In Vienna, politics is quite clear about green gases in the heating sector. So we see green gases as too valuable to be directly used in the gas grid for direct heating of boilers in flats. So we don't want to waste this valuable good in sectors where other alternatives are given. But as you can see here, the district heating share will be increased additional to a reduction of energy demand. And this district heating will be provided on the one hand by geothermal energy and large heat pumps. So you can see electricity again, but also to a certain share by gas. So as you can see, for the provision of district heating for the whole city, we will need gas. A lot of different technologies. On the one hand, base load technologies, as you can see here in the annual progression of the district heating demand in the red curve. The base provision of energy based on waste to energy, for example, and geothermal can cover certain parts of the energy demand or the heat demand, but there are some lacks, especially in winter times, in cold times, where you need something else, something more flexible. In this load duration curve, where you can see the daily amount required in the district heating system or in the district heating in descending order of magnitude sorted, you can see that the orange part and the brown part over there is covered by gas still. That is because we need, in these cold times, in winter times, flexible options. We need something to cover the peak loads. And we need something else, as you can see here in these areas where the blue areas are interrupted, that are times when the electricity price is really, really high, then it's not economic feasible to operate heat pumps. And in these times, green gas gives us the flexibility to provide heat, achievable and affordable heat by good prices by operating combined heat and power plants in these times. So this is not only a technical flexibilization, but also an economic flexibilization option. So to sum it up, we calculated in this ideal decarbonized system that we will need about 4 terawatt hours of green gases compared to the 20 terawatt hours of natural gas we are using now. It's quite a low number. But on the other hand, there are studies, for example, for a whole area of Austria that the green gas, achievable green gas amounts is about 20 terawatt hours all over in Austria. So we have to think about where these green gases come from. We will need it for several applications, as I've already said, for combined heat and power plants, for certain applications in mobility in a small share, and especially in the peak load times of heat generation for the district heating system. And we need every option to get to this 4 terawatt hours of green gas. So we haven't fixed yet how the shares of hydrogen and methane in this mixture should be. For example, we're testing at the moment hydrogen in combined heat and power plants to a certain share, but we will need this amount. So finally, I would like to talk to you about gasification and why we are interested in this technology. As I've already mentioned, we are processing about 1 million tons of waste of the city of Vienna each year. And we have heard that we will need green gases and green fuels for all these applications to achieve this vision of Decarb Vienna 2040. And we see a large opportunity in utilizing materials what we use now at the moment just to generate heat in the form of waste energy plants, which provide base load capable energy, but are not storable and not flexibly applicable. Whereas gasification could lead to energy carriers, which are much more storable and homogeneous and flexible in application, and also are compatible with the energy system at the moment. For example, our combined heat and power plants at the moment. So that's the reason why we're interested in this pathway, because we have resources which could be in the future utilized in other ways than just burning it. But we see that this technology or this process chain is not commercially available, that you have many suppliers to choose with, because we're, for example, owned by the city of Vienna. We have to do certain procedures to buy, for example, a plant. And there are several technical risks, technical questions which have to be answered. And we don't have the right data to know how to integrate such a technology in our energy system and how we can calculate, for example, business case. That's the reason why we decided to participate in a research consortium, which built under the consortium leader BEST, Bioenergy and Sustainable Technology, 1 megawatt demonstration plant demonstrating a process chain from waste to value, that's the name of the project, gasification and synthesis for a contribution to this vision of the city of Vienna of tomorrow. So if you have any further questions regarding the research project, I'm happy to share information about that or our vision of the city, and I'm happy to answer all the questions. Thank you very much.
Thank you very much, Teresa. Well, there is a question in the chat. People are asking, well, why not earlier than 2040 fully sustainable? So perhaps you can rephrase that question by asking, well, what are the, let's say, rate limiting steps? What are the limitations not to do it earlier? You're muted, Teresa.
Sorry. I think in Vienna, for our point of view, or our framework, our conditions, it's quite ambitious because we have, for example, to invest largely in renewable electricity production. The ramp up takes time. We have other issues, for example, in regard of waste to energy plants. We build a roadmap at the moment for making them carbon neutral, and it has been seen that 2040 is quite ambitious. So I think it's in our regard quite ambitious, and I don't think that earlier would be possible.
Okay. People are also curious about the let's say the gasification demo project, and also what happens next. But perhaps it is good to answer these questions in the chat, so or in the Q&A. So perhaps you can have a look at the Q&A and provide some answers to those questions there. Yeah, is that okay? Okay. Well, perfect. Thank you very much, Teresa. Then we go over to the next presentation. The next presentation will be, let's say, a slightly different perspective, still an industry perspective, but from a technology supplier, from Siemens Energy. And it will be Markus Jucker who will give the presentation. He's the research and technology team leader for gas turbines at Siemens Energy in Sweden. And his presentation is entitled Gas Turbines for Sustainable Energy Systems. Markus, the floor is yours.
Okay, thank you very much for the introduction. Hope you can hear me well, and I share my presentation now. Okay, do I share my presentation?
Not yet.
Share. No, now it should work. Right?
Something is happening. Yes, now we see it.
Okay. So thank you very much for the introduction. So I'm from Siemens Energy, and of course we are a company. We are fully committed to the net zero targets, and want to provide technologies and solutions for that. So I put together a presentation here from a gas turbine perspective. So I will start to talk shortly about gas turbines, because not everybody may be aware of what a gas turbine is and how it works. And then I will go into the topic of the fuels, which kind of fuels we are looking at. And that is then, of course, interesting, very interesting for this workshop, how we see on the bio-based fuels also. I will talk about testing. How do we test our turbines and where we are? And finally, I will also talk a little bit about the market. So what are the market ideas and perspectives we have? So I start with a gas turbine. So this is an example of a gas turbine, the SGT 800. And I will talk mainly about the medium-sized gas turbines in this presentation, because I'm now working in Sweden, where we produce these gas turbines, but many of these conclusions will be probably also valid for other gas turbine sizes. So simply, the gas turbine consists of a compressor, a combustor, and a turbine. And it's a gas turbine because the working medium is gas. So when the gas turbine is operated, you suck in the ambient air and compress it in the compressor. And then in the combustion, you mix the fuel into the air, and then you combust that in the combustion chamber. And then the gases becomes, of course, very, very hot. And then they are expanded through the turbine. Normally you have then quite hot exhaust gases, and they are normally utilized in different applications. For example, in a combined cycle, then you would use them together with a steam turbine to increase the efficiency. Then you can come up in a combined cycle in efficiency is about 60%. And we also heard about here the combination with heat and power production. So if you also take out the remaining heat, you can come to more than 90% of efficiency in such combined heat and power plants solutions. So some technical characteristics. So normally the sizes are between 1 and about 600 megawatts. That's at least what the range of gas turbines we have in the Siemens Energy portfolio. These machines are characterized by a very high power density, of course, and then also combined with low emissions and high efficiency. Gas turbines can be started very fast. So normally we have 10 minutes of startup times. We are looking at even faster startup times. So that's completely different to steam turbines, where there's much more metal to warm up and are slower to start. So normally you can operate gas turbines very flexible, and this is of course beneficial with the challenges we see on the grid systems in the future. I also already mentioned the hot gas exhausts, which can be utilized, so we get a large benefit out of the fuel. I think we all agree that the fuels in the future become very valuable because they have to be produced from, for example, from biogenous sources. So then we should also make sure that once we burn it, we should use it to as close as possible to 100%. And the final point is a gas turbine can run very fuel flexible. And that is a major topic for this discussion today, to show how fuel flexibility can be achieved. So here you see the key element when we come to burning the fuels, and that is the burner itself. So here you see our third generation DLE burner, which comes with very low emission values. And you see here the three gas turbines, which all have the same burner, but they are in different sizes, power ranges. So of course, if we make a further development on one of the burners, it will automatically be applicable to all the other gas turbines with their burners because it's the same system. So the SGT 600 to 800, we are talking about a range of between 20 and 62 megawatt power output, electric power output, yeah. So that is maybe important for orientation also. So another aspect which I want to highlight if you talk about gas turbines, so only talking about the gas turbines which are supplied out of Sweden, there are more than thousands in the world. And that means also that there is an infrastructure already existing, which can be used to transform the energy system to a sustainable system. I think that is a value which should be not neglected. So a lot of the assets which are there could be used and in another way and make them climate neutral. Yeah. Okay. So now I want to talk about the fuels. So here is just an overview of different fuels we are looking at. I guess you in this workshop are much more competent to talk about the processes, how to produce these fuels and what are the different technologies behind that. For us as a gas turbine manufacturer, it's of course very important to understand the composition of these fuels and the quantities of these fuels which will be available. So of course, biomass and biogenic fuels are very interesting for us, but we are also looking, of course, on other fuels. Hydrogen is very important, so it is a technical challenge to come to the 100% hydrogen capability. But we also look at different e-fuels and also on the other alternatives here, and I will come to it more details then. Just before that, I just want to show that the capabilities we have today. So today we can burn up to 75% of volume of hydrogen in all our, or most of our gas turbines. That means translated to energy content, it's about 50% of the energy content would then come from hydrogen, and the rest from the other gas which is mixed in. And we have very ambitious targets now. Until 2025, we want to ramp this up to 100%, and we are working on that very hard to do that technology development. Okay. So, but then this needs to be tested. So normally there's a complex procedure to develop this. So it normally starts on the table, and then you do some benchmark tests before you test it in the real life, and finally in a real engine. In Sweden, in Finspång, where I am located, we have the manufacturing capabilities here, and that comes also with testing capabilities. So you see here the site, a recent picture where you have a turbine testing facility normally used for our customer engine tests, but we also use it then to verify some of our technologies. But of course, the fuel supply is a difficult part of it because, I mean, we are not an energy supplier, but we are a turbine manufacturer. So one recent project we had here is the Zero Emissions Hydrogen Turbine Center, where we built a demonstration plant to produce our own hydrogen. And that's what you partly see here on this picture, which is integrated with solar panels and an electrolyzer and also a battery and hydrogen storage. So with that, we are becoming more independent, and we can produce our own hydrogen, which we then use for testing. And I want to show you quickly also the concept behind that Zero Emission Hydrogen Turbine Center. So when we normally do our gas turbine tests in that gas turbine testing center, we would produce a lot of energy, which we would need to partly feed into the grid, but then also waste a lot of that energy. So today we can use some of that energy to produce our own hydrogen and store it, and then together with the solar panels and with the battery storage, we can then integrate it to a kind of a microgrid, just to demonstrate how such a system could work. Of course, it's a very small scale here, but we have successfully demonstrated how it could work and that it could be scaled up. And then we'll come at the end of the presentation to an example also how a scale-up model could look like. Okay, excuse me. So I think this here is an interesting picture because it shows the green fuels roadmap we have on our in front of us. So I think it's also important to mention that this roadmap to realize, we are really looking for collaborations and partnerships. We can't do that alone because, as I mentioned, it is hard to. It's much easier if we have a customer where we can operate a gas turbine in real conditions. Momentarily, a lot of focus is on hydrogen. So where we are today capable to burn 75%, but the near-term target is 100% already in 2025. If it comes to biogas, we can already burn it today. It's not normally very close to natural gas composition. On then we also look at the ammonia track. Here we look mainly on the option to use cracked ammonia. So then from a combustion perspective, it becomes more similar to hydrogen combustion. And we see that as a possibility once the storage size of the hydrogen storage becomes too large, and then ammonia could be another option. But when it comes to liquid fuels, we are already since a long time we can burn diesel, and now we have also verified that we can run on biodiesel. So that is, of course, a very nice option, and it's also to demonstrate that flexibility. We can use both fuels in the same engine that we call the dual fuel option. So you can have one engine and you can operate it both on some of the gaseous fuels, but also on a liquid fuel. So that's always very important for our developments, that we always keep that flexibility of the operation. Yeah. You see also in the long term, we are looking at other liquid fuels and also at methanol and ethanol. That's just a prioritization, what we think is the most important right now to prioritize. So here are a picture about testing. So we had a close cooperation with the power plant in Ria. That was last year. And this cooperation, we could demonstrate different biodiesels and finally release 100% the HVO as a approved gas turbine fuel. Another interesting reference is the Stockholm Exergi project, where there is right now a gas turbine installed, and that gas turbine shall operate fully as a backup power plant, and shall be operated fully on biofuels, on biodiesel. So that shall be going operation 2023. All right, so some words also about the market. So you know that the gas turbines can provide a lot of services to the electricity market because of its inertia, and also because of its flexibility. And we also talked about that by using it both for electricity production and heat production in combined heat and power plants, you also get a very high value out of the fuel you put into a gas turbine. So we think there is a place for gas turbines on the market. So it's not the same place that is today. It's not a base load engine anymore, but it's more as a backup engine, as an engine which provides different services in primary and secondary response, and that together with different kinds of climate neutral fuels. Yeah, and I think everybody is aware of the situation that once the renewables are increasing, and you have seen that in the previous presentations, there will be times where you have long durations without wind and solar. And in a shorter period of times, that is probably the batteries are the better choice, of course, if you have maybe 4 hours to buffer. But if you talk about days of lack of energy power, then you need other solutions, long-term storage solutions, and gas turbines with different fuels can play a major role there. Okay, I also want to shortly talk about a very interesting study which the University of Gothenburg did in Sweden. Gothenburg is a partner in that CEHDC project we have together, and they are looking actually at the role of gas turbines in the future, if there is a role, and how it could look like. So many of the conclusions we have are somewhat related to this study. And it's also interesting for this forum here that the study looks specifically also on the influence of biofuels on the market. So of course, there will be an interrelationship between the availability and costs of biofuels and the availability and costs of hydrogen. So for us as a gas turbine manufacturer, the conclusion is very clear. We need to provide gas turbines which can handle both, to provide our customers the most flexibility to operate the gas turbines on the fuels available. All right, and now I just want to finish with a small study we did also in Siemens Energy here. Just imagining that a society which may be 250,000 inhabitants, just to scale up this zero emission hydrogen turbine center to a large scale. And it's very clear this is just an example, and we know that every location, every condition might be different, but we found it very valuable to visualize a little bit how such systems could look like. So that, because then you start thinking and how would that look like in my situation. So we see that gas turbines can play an important role when you have more wind-dominated systems, and so we did that here for such a system where you have maybe a wind park of 600 megawatt and a solar park of 300 megawatt. So then you would still need some battery support to buffer for the short durations, but then you would need a long-term storage, and the size of this long-term storage we calculated here. So with one power plant, a combined cycle power plant here of 89 megawatt, you would need a hydrogen storage of 150 tons and the electrolyzer capacity of 160 megawatt to make this a sustainable system. We also see, I mean, if storage needs would be larger, that you would need a hydrogen storage of which lasts more than 2 or 3 days, then it becomes not feasible anymore to have hydrogen storages, maybe. And then we would suggest other storages that, for example, other liquid green fuels could be used as a storage medium. But of course, that's again, it's different from case to case, and this is just a food for thought, so that how such systems could look like in the future, and we work on to provide the technology to realize it. And also, okay, I think that was all I wanted to say. So thank you very much for giving me the opportunity to talk here, and I give it back to Jaap then. Thank you.
Thank you, Marcus, for this interesting presentation. I know that, let's say, it's in no way straightforward to make gas turbines that can deal with such a wide range of gaseous fuels and liquid fuels. So I think that's quite an accomplishment. To what extent have these new concepts already been introduced in the market, let's say at commercial scale?
Yeah, I think it's introduced. So we sell gas turbines which are future-proof for 100% hydrogen. Even the technology is not fully developed yet. You saw the example in Stockholm, where there is a backup power plant where we committed to 100% biodiesel operation. So I think we have it's commercially viable, and we have customers interested in this, and then we're selling it also. Yes. Okay.
Well, then there is a question in the Q&A on what are the challenges to go to 100% hydrogen?
I think hydrogen, everybody can imagine that it burns very fast. So the flame speeds become very high. That means, simply talking, you need to have very high velocities in your burner to make sure that the flames are not traveling backwards into the engine. That's what's called flashback. So that is one major challenge. Then you have also challenges with the stability. So the flame stability to make it all the time stable combustion system. So it burns very different to other fuels. And for us, of course, then we need that the same burner can burn both natural gas or biogas and hydrogen. So you always need to find that compromise to make it work for everything.
Mm-hmm. And how is that with let's say bio-based feedstocks, for instance, like methanol and ethanol?
Yeah, we started testing that. So, but you saw on the roadmap, we put it a little bit further ahead because we don't see it right now that our customers are requesting it actively. So, but we have it on the radar, and if there should be interest is increasing, we will of course also develop solutions for that. I think yes.
Mm-hmm. So you envisage that also in the future. You can do with one burner design for this whole range of feedstocks.
Yeah, I'm not sure about ethanol and methanol. It's too far away. I mean, we sure ammonia is a very different fuel. So I think here I'm quite sure we can't do it in the same burner. So that would be a completely new development. Ethanol and methanol, I'm not sure. I would need to talk to our combustion experts also. But it's a little bit further down the road. Yeah.
Okay. Well, thank you very much, Marcus. There are a few additional questions in the Q&A, so perhaps you can have a look at that and provide answers there.
I will do that. Thank you very much.
Yeah. Once again, thank you. And then we go over to a man that has a difficult task, because we've now seen in various presentations that flexibility provision from bio-based options, even narrowed down to gaseous bio-based fuels. That is quite a wide range. There are many possibilities, and so it is not an easy task to shed some light in, well, how to structure them, how to structure these different options. Still, Tilman Schildhauer from Paul Scherrer Institute in Switzerland, also being one of the representatives in Task 44, will do an attempt to, let's say, structure all these different options. And so in that sense, give an overview of the various concepts, technology concepts there are. Tilman, the floor is yours.
Yeah, thank you very much. I hope you can see the slides the right way.
Yes.
And so before we now later deep dive into the even more technical options which we have with biogas and gasification, I would like more to give an overview of all options which we have for flexibility in bioenergy. And and by do that, this is, I would call it as a kind of a landscape, and this an idea or attempt to actually somehow order the whole system. So we see we have some feedstocks, there's wet biomass and there's dry biomass, and it's kind of obvious. Dry biomass like wood or so you can store for quite a while. Wet biomass often is not very good storable because it decays and forms maybe CO2 or methane in the wrong place. There's all kind of applications which we have on the right hand side. We want to have heat and electricity. We want to have fuels for transport mobility. We might want to have some chemicals, and we might also have to want some biogenic CO2, which we actually can then sequester and store it for a very long time, so to come actually to negative emissions. And on the way in between, we have actually intermediates and we have energy carriers. And the biggest difference is intermediates are things which we can transport only for a short distance or store only for short times, and we have energy carriers where we actually can store for a longer time, and we have also more transport options, so there's way more infrastructure available. And if you look in what we have there, then we clearly see there's product gas from gasification, which is intermediate. Biogas is to some extent an intermediate, and also pyrolysis oil, although pyrolysis oil already has a tendency to be an energy carrier depending on what the timescales are. For the energy carriers, clearly we have liquid fuels like methanol, ethanol, gasoline, diesel, things like that. We see methane, or in the liquefied form is LNG, or then bioenergy. Clearly there's pellets, ships, biocoal, and stabilized pyrolysis oil. Now, if you look how we get from one to the others, and the arrows in between these are the technologies which are available, and maybe later we'll hear way more about it, at least about some of them. What I would like to introduce here a little bit also in this overview is that we have different actually ideas what we could do with this flexibility, and this concept was already discussed by Lina at the beginning of our webinar. We have this long-term flexibility where we actually translate bioenergy into something which can be stored and can be used at different times at different places. And we have more the short-term flexibility, which mainly is about the connection to the electricity grid, where once we have a positive ancillary service, we can supply electricity when it's needed, or we can take up electricity when there's too much in the grid at the specific point where it's used. And this is about what you can do with that. But if we looked, when we looked through all the technologies, we recognized they are not all at the same status. So there are some, and I show them as green arrows. We have technologies which are existing, so they work technically, and they also have business cases, so they're applied at many places. We have some which are, I call here emerging technologies, so technically they work, but so far they have not found a business case yet, and that is a kind of a, let's say, ambiguous discussion, because especially now with the war in Ukraine, we see that many technologies which we might have expected to come in 5 or 10 years, maybe people now are interested to have them earlier, because now there's quite a different, let's say, emphasis on energy supply security, which makes some of the technologies more attractive. And I would not be surprised if some of the technologies actually jump from yellow to green in the next years because of this aspect. And then we have technologies which clearly are at lower TRL and still under development. If we now start with the landscape, I would like first start with the biogas. We hear way more about that before, but this is one of the technologies where everything is already quite applied and seen in many places. So we can actually take wet biomass, convert it to biogas, mostly by anaerobic digestion. The biogas can be used right away in combined heat and power plants. There's some flexibility options. Or we could upgrade it into methane, which then could be injected into the natural gas grid or liquefied, and then use both for CHPs at different places or for mobility. And there's clearly, if you do the upgrading, there's two options of doing that. The more classical one is I just separate the CO2. At the moment, mostly it's given to the air, but in principle, we would be able also to collect the CO2 and transport it to sites where we can do actually sequestration, so that we have negative emissions by the CO2 from biogas plants. Or the other option is we can actually add hydrogen to the system. Then you need a kind of methanation reactor which actually converts the CO2, which is too much, into additional methane. So these are the two options. Clearly something you could do if we have more electricity than we need, and we can produce hydrogen by electrolysis. So these are the common ones. Also, if you have burned the methane or the biogas in a CHP, we could actually use the CO2 also for negative emissions here. But this is actually connected to additional cost, because we have to collect the CO2 or separate it from the nitrogen first, which causes some cost. There's other technologies to convert wet biomass, which are more under development. And these are mainly hydrothermal processes where we actually can go either to pellets or chips, could also be kind of torrefaction, or where we go in the directly to some liquid fuels, which then can be upgraded along the more classical ways to chemicals or transport fuels. If we start from wood, the other main energy or bioenergy source which we have, then there are a couple of very classical ones. So the more classical is actually the combustion. So if we produce some pellets or chips and we burn them in some CHPs, We might also produce biocoal this way, which then could be used for negative emissions. That is a very recent technology development, still under development. There's clearly gasification of wood to form product gas, and then use of the product gas in CHPs again, in gas engines, also very classical. And something which now is really making the jump from yellow to green is the production of pyrolysis oil, which then has many different options. It could be stabilized, and it could be used for CHP production, could be used for heating. So there are many options from that side. And for the stabilization, again, there is some hydrogen needed. If you take all that together, there's even more options for product gas. We can do, when we did the gasification, then we have actually a gas mixture which is very similar to syngas, and that offers us all the options of syngas chemistry, where we either go via methanation to more methane or liquefied natural gas, or to liquid fuels like Fischer-Tropsch from methanol. And again, like in the biogas case, if you look into the composition of the fuels, then they're usually oxygen-free. Biomass is not oxygen-free, so there's always some production of CO2, which we either have to separate, and again, we could do negative emissions with this CO2, which we have to separate anyway, or we add hydrogen and produce more of the fuels which we would like to have. And this is definitely still under development. And if you really want to be very flexible, you could even use the same plant, and when you have too much hydrogen or enough hydrogen, then you do the additional synthesis. And if you do not have, you separate the CO2, and you can make at least part of the carbon into a negative emission. Altogether, this is a big network with many options and many different states where we are. If you conclude a little bit what we learned from that, many technologies exist and they work, and the ones where also the business cases work is the standard is wood combustion that worked since ever in human history, but other business cases which work start usually with waste streams, especially those which do not burn, and all the processes where we can actually produce electricity if you have good scheme in place which actually adds to the or supports the extra cost from that. Then usually you have a tendency to operate them at long times, but with some additional support for flexibility, and we will hear more about that. Then that can be also used very flexible. So it's really starting now. Wood, as I said, usually is combusted. You can use it as a feedstock for all kind of other chemicals, but there you're always in fight with other feedstock, especially fossil feedstock. So which made business cases, for example, wood to diesel or wood to natural gas, quite difficult now. But here we might see that in the next years that might change, because the need for security of energy supply actually could change the picture. The reactive hydrogen addition is something which works, but is still under development. And if you take all that together, flexible peak electricity production, negative emissions, the option to take up electricity when it's not needed in the energy system, that's are really important building blocks which can be delivered by energy. So in principle, it's a good thing, but many of the features so far I actually underestimated what the value could be for the energy system, and we hope it's going to change in the next years. There's a table with all of these technologies. I'm not going to bore you to read all that. You will be able to read the slides anyway later, and I would actually would like to end and make you aware of that we wrote down many of these technologies. We made a report about that with the support of all the other tasks on gasification, on combustion, biogas, biofuels, and so on. That can be downloaded from the homepage of IEA Bioenergy, and there you can read even more in detail about all these technologies. And with that, I would like to thank for your attention.
Thank you very much, Tilman. Well, I think it shows from the questions in the Q&A as well that it is almost impossible to let's say, collect and structure all possibilities with respect to flexibility options. You did quite a good task, but there are some remarks concerning, well, perhaps there are even more options if you dive further into the material system. I think you will agree to that, for instance, by using fibers, the fiber part of the biomass.
Yeah, absolutely. I mean, we looked here into bioenergy only, and if we can use biomass for some material use, then it's usually preferential. I mean, the best is making buildings, furniture, or using for fibers for something, for some even higher value products than energy. I fully agree on that. It would be also always my first choice. And then we should actually focus on the leftovers from these processes. Whenever we make a high value product, material product from biomass, there will be some waste streams. And these again are interesting feedstocks for us. I think that is quite clear.
Yeah, and perhaps you agree that we, in that respect, when considering, let's say, the integral energy and materials system, we're still in a rather early phase with respect to exploring all the possibilities and then not only exploring them, but also shedding some light on what would be the preferential routes.
I fully agree here. I think also that there will be never one big solution like this perfect biorefinery concept or so, which actually has to do, I mean, there are so many different pathways because there are different biomasses, and usually biomass is distributed, so logistics are very different, very difficult. So sometimes it just makes sense, take the bioenergy which you have, because it's a small amount, do something, even if you burn it, no problem. If you don't have a better use in that region, then it's most probably the best option. So that really strongly not only depends on technologies or efficiency, also the logistics play an important role, and also the infrastructure which is available, because the answer what to do with biomass could be completely different whether you have a district heating system or a natural gas grid in a region. So that is really depending on logistics and existing infrastructure. So that makes bioenergy very interesting for engineers, but sometimes a little bit difficult to communicate what to do best.
Indeed. Well, with that, Tilman, thank you very much. There are some more, let's say, specific questions in the Q&A. Perhaps you can address them there. And with that, well, you're not completely done, because we have a Slido question. And perhaps, Marco, you can put that on. And that concerns what are the main challenges for flexible bioenergy? And again, multiple answers can be given. So please, all the participants, if you could address this question and shed your light on these challenges. And it's clear, I think, that it's not only technical challenges that may be considered, but especially also non-technical ones. And I think in the workshop up to now, we've addressed mainly the flexibility options from a technical side, and we will also keep on doing that in the remainder of this workshop. But here also some non-technical issues are mentioned, and it's interesting to hear your views on that.
Yeah, let's see what the audience thinks.
Yeah.
Okay. Again, a kind of an equal distribution, but clearly the CapEx question is an important one, which most probably inherently has to do with the fact if you do something flexible, it means we need a capacity higher than, or we don't use all the capacity which is installed all the time in the market pool. Yeah, that's a difficult one. I'm kind of happy that people somehow believe that the technologies are working. So less people believe it's a technical problem. It's more on the commercial side and on the market side. Very interesting to see it this way. Thank you.
Yeah. Indeed, in many cases, flexibility comes with a cost, and I think also in the audience, people recognize that. Well, thank you very much, Tilman, for your contribution. And then we go over to the, let's say, the different technical options. We dive further into them. And we will do that by involving two tasks leads from other tasks of IEA Bioenergy on gasification as well as on biogas systems. So we will dive further into the technology options for those two, let's say, technology routes. And we will start with the gasification option. We've heard on that already some thoughts and some ideas and concrete plans from Biogenic in Austria. But now we will, let's say, address it in a more general sense. And that will be done by Berend Vreugdenhil. He's also from TNO. He's a senior scientist there responsible for the gasification and pyrolysis activities at TNO. And as said, he's as well the task lead of task 33 of IEA Bioenergy on the gasification of biomass and waste. And he will give a presentation on the flexibility options from biogenic gases with a gasification perspective. Berend, the floor is yours. We cannot hear you yet. Still, we do not hear you, Berend.
You hear me now?
Yeah, now we hear you.
And you can see my screen?
Yes.
Perfect. Okay. Thank you, Ja, for your introduction. Yes, my presentation is about the gasification perspective to this all. I'm the task lead of IEA Bioenergy Task 33. First, a very small introduction to the task. It's a collaborative workforce with currently 12 member countries participating in this task, where we share knowledge and information on gasification developments within our countries. We try to support industrial activities as much as possible, and we're always looking for new member countries to participate if possible, of course. So if you need any further information and you are part of one of these countries, just reach out to your representative and they will help you further. So within our task, we focus on gasification, and then this workshop is on flexibility. With gasification, you have a lot of flexibility to start with. We're very flexible towards the different types of feedstocks. We can deal with solid biomasses, with waste streams, with wet biomasses like sludges and manure. And then there's flexibility towards technology. So the conversion technology for the feedstocks and the gas cleaning. You can build all kinds of production pathways, either directly to one product or co-production schemes. But more importantly, I think also for this discussion is you can integrate it with other renewables, such as hydrogen from a surplus of power. And then the hydrogen can be utilized, especially in these high-end applications where there is typically a surplus of oxygen in the feedstock, leading to a surplus of CO2 in the gases, and then that can be utilized by adding more hydrogen into products. And we're also strongly focusing on CCS, on negative emissions, by either sequestrating the CO2 in case you don't have hydrogen available, or looking into utilizing the biochar that is produced in certain processes. But for now, for this workshop, I asked my members to provide me some cases on flexibility, and I got 3 different production pathways. So going to green gas, going to methanol / DME, and going to Fischer-Tropsch products via gasification. And then within different projects, they evaluated what the feasibility is of utilizing electrolyzers to produce hydrogen and to increase the yield. And this turns out to give some nice results. So first of all, within gasification, you typically start with a biogenic residue, forest residues, agro residues, or even household waste. And via gasification, you produce a product gas. And this product gas, based on the technology, can consist of, well, the main constituents is CO, hydrogen. There's always CO2 and certain amounts of methane in there. And if you have a direct gasifier using air, you get a lot of nitrogen. If you have an indirect gasifier, you have a low nitrogen content, and with an oxygen blown, also a very low nitrogen content. Then if you look into the feedstock, you already see the issue. The biomass feedstock is mostly carbon, hydrogen, but also a large part is oxygen, and this oxygen will bind to the carbon to form CO2 in the process. And if you go to fuels, typically, if you go to SAF, you have a CH2 as the main fuel composition. If you go to methane, it's CH4. So there's a deficiency of hydrogen to valorize all the carbon. That's one of the issues. Then solving this problem is by introducing electrolysis. Then in this case, they evaluated a dual fluidized bed gasifier where you don't use oxygen, but you use air in a separate mode to combust char, which is then reheating a bed material, circulating in this dual fluidized bed gasifier, producing a synthesis gas. And the example that was presented by Vienna, by Schubert, she mentioned the waste to value process, and there they use this technology actually. But there again, you have a synthesis gas which is, well, quite suitable for Fischer-Tropsch, but not for methane production. So you need hydrogen, and the hydrogen can then be added from an electrolyzer. You produce hydrogen. You can even add the oxygen in this case to the gasifier. So you can also utilize the gas, the oxygen in the gasifier, and also you can utilize the heat in the overall liner. So what are the advantages if you're producing a green gas? So making methane out of a synthesis gas is, in this case, you really valorize all the carbon that is ending up in your product gas. You can more than double the product output, which leads to a higher overall process efficiency. It's also a way to utilize the oxygen from the electrolyzer, which doesn't have to be high grade, because it goes into a combustion zone and it produces a separate flue gas. The hydrogen addition also avoids the use of a water gas shift, because you have to go to a higher hydrogen to CO ratio than is produced in your gasifier, and by adding hydrogen you actually can avoid this. You can also avoid a large hydrogen storage, because you're using the grid to store hydrogen, but then bound to a carbon atom. And it's also very flexible, so it doesn't rely on a steady load of hydrogen, because it can produce methane from its own synthesis gas. It's just a way to increase your output if there's a surplus of electricity. So in that sense, it's very flexible towards the operation mode of power generation and then conversion into hydrogen. And they evaluated a case. Ilka Hannela published this already quite some time ago, but basically you start with 100 megawatts of feedstock input, wet biomass, and there he calculated that without the addition of hydrogen, you would produce about 64 megawatts of SNG of methane, which is more or less in line with what we see with the Güssing gasifier, where they produce methane, and the Go by Gas project in Sweden, which roughly had a efficiency of 65% towards methane. But then by adding hydrogen, you could go to 140 megawatt, because the CO2 that you have to take out of your process in order to be able to inject it into the grid can now also be converted into methane. What's interesting is that you actually need, compared to the amount of biomass, a significant amount of electricity, which is converted into hydrogen. So you need 140 megawatt of power for the 100 megawatt biomass starting point. And I think this shows the potential of storing surplus electricity in bioenergy processes. The second example was provided by Sweden on the LTU Green Fuels plant, which was a demonstration plant which was built already back in 2005, started operation. It's a 3 megawatt plant operating on 20 tons of dry solids per day. In this case, black liquor from a pulp and paper facility next door. So they provided the feedstock. It was then converted into synthesis gas and after gas conditioning converted into methanol and DME. So they had two processes which could be demonstrated with storage and distribution attached to it. And they operated that downstream process for over 12,000 hours since 2011, producing quite some methanol and DME. And the interesting part is they demonstrated that the cooking chemicals that were used in the pulp and paper industry could be recovered in this black liquor gasifier. And they also demonstrated the co-gasification of pyrolysis oil from a fast pyrolysis process, tested over 1,000 hours. And there you see what I mentioned, the flexibility towards feedstocks, that you can you don't have to rely on one specific feedstock. And for this process, they made the same calculation, and these are the numbers. So basically, they translated it to what they thought as a feasible plant size for a pulp and paper installation, having roughly 50-50 black liquor and pyrolysis oil as a feedstock. Then they calculated that they could produce 330 megawatts of product, of methanol. And if you would add hydrogen, and there you see you roughly need a similar amount of hydrogen to valorize all the carbon that is in the product gas. But that also means that you need quite a large base load of electricity, so 800 megawatt electricity production to produce a sufficient amount of hydrogen towards the methanol process. When I was looking at these numbers, it shows the potential, but also the challenge that do we think it's feasible that such a large amount of electricity would be available at one specific site to produce this amount of hydrogen. But the good case is that in these catalytic processes, it's easier. It's quite flexible to operate with an increase of hydrogen by just tuning your CO2 removal in order to have the right ratio for the methanol synthesis, similar to the methane process. And this is the way they introduced hydrogen in the process, is similar as the methane approach, where you just you add hydrogen where you can valorize more of the carbon which is in the product gas. The third pathway that I would like to quickly go over is the Fischer-Tropsch pathway. Was also calculated based on the dual fluidized bed gasifier, which actually has a ratio of hydrogen to CO, which is optimal for Fischer-Tropsch synthesis. So adding more hydrogen would not make sense in order to because it would destroy your ratio. You don't have the CO. But what they did here is that they recycle the CO2. So downstream the gasifier, after cleaning, normally the CO2 is an inert in the Fischer-Tropsch process. And in this case, they would take out the CO2 and add it to the gasifier, replacing steam. And by adding more CO2 and having less hydrogen, in fact, your water gas shift reaction would produce more CO. So you would be off spec for the Fischer-Tropsch process, but that would allow you to introduce the hydrogen from the electrolyzer. So this is actually an elegant way to utilize the CO2 that you have to remove from your process anyway at some point. Here this is then the the starting point for the Fischer-Tropsch synthesis in this case. And yeah, the Fischer-Tropsch process is not aiming to produce one specific product. It's a whole distribution, the Anderson-Schulz-Flory distribution, which gives you everything from C1 to, well, here you see up to C30, C40 molecules, mostly alkanes. And then you have the different specs. So you have a part gasoline, a part diesel, and you can take out the part that goes to SAF. And then you have the waxes, which typically are upgraded to produce more fuel. Yeah, so this is calculated by again Ilkka Hanula from VTT back in the days, and what he calculated. So what he worked on is using the additional hydrogen to double also the Fischer-Tropsch products, leading to a higher carbon utilization. And if you look into the diagram later, you will see that in fact you need much less hydrogen to utilize it. A little slide on the advantages of Fischer-Tropsch liquids. It's compared to diesel or the traditional way of producing fuels from the petroleum-based is containing a lot of impurities, and combustion leads to, as you can see, not a flameless flame, but a lot of pollutants. And this is, well, I think one of the drivers also to go to the ultra clean Fischer-Tropsch diesel, as Shell is promoting this, but also from a bio-based process, this would result in this clear liquid. And it's also a way to go to drop in SAF feedstock, so you can replace conventional jet fuel up to 50% if you make this nice clear Fischer-Tropsch liquid. So that's a big advantage of producing Fischer-Tropsch. And then this is an example which was worked out in more detail, where it was called the wind diesel project, where they evaluated exactly this process of having the CO2 removal and then replacing steam in your gasifier, which means that your product gas is now off spec and allowing you to introduce more hydrogen to valorize more of the CO, which is then in fact shifted CO2 back to CO, convert that into Fischer-Tropsch products, and then you can go to diesel and kerosene. And here they calculated the base case, starting with 100 megawatts of biomass, you would be able to produce about 50% Fischer-Tropsch products, which could go up to 88 megawatt Fischer-Tropsch products by adding electricity, in this case from wind. That was in this project the evaluation how to integrate excess wind energy with a Fischer-Tropsch process. And in the link you can find a little bit more information about that. So what I did for these processes, I calculated them all back to 100 megawatt thermal biomass input to get some idea on the numbers. And then you see for green gas and for methanol, the efficiency is the highest. I think in general, if you go to methane, the overall efficiency would be probably the highest. You can go up to 70%. I think methanol in this case would be already at the limit of what is technically feasible. And this, I believe, is also more or less the accepted. Maybe it could be increased to 55 megawatt Fischer-Tropsch product, but there you see the limitations in yields towards the end molecule. But I found the interesting part is also the consumption of electricity needed to valorize all the carbon in your product gas. That you need, compared to your biomass input, a lot more electricity to valorize all the carbon, and then also leading to more than double the output. And in case of Fischer-Tropsch, it's actually less. And I was thinking about this, and I would say the reason is that you need less hydrogen to make CH2, a linear alkane, compared to a methane as the end product. So going to methane allows you to capture more hydrogen if you have a surplus of electricity. I think what these these three evaluations shows that there's various upcoming pathways that can generate a lot of flexibility for a surplus of electricity, not only from the molecule side, but also from the heat. The electrolyzer will also produce heat that can also be integrated into your process. You can also integrate the oxygen from electrolyzers. But it also shows that if you aim to valorize all the carbon that comes out of a gasification process, and my personal feeling is that a commercial size plant will roughly be 100 megawatt or up to 500 megawatts, where some projects aim, like the biofuel project in France aims to go to 500, 600 megawatt plants. Then you see the amount of electricity that you would need to valorize all this carbon is quite nice. So I wrote down a question maybe for people working in this field. If you have a limited hydrogen availability, what would be the best way to utilize it? Is it maybe not towards SAF? Because first of all, you need less hydrogen to valorize more of the carbon. And secondly, SAF is one of the toughest to decarbonize products that we currently have in our energy transition. So focusing on more output there maybe is a better choice. Then my last slide is a concluding slide with an actual project in the pipeline, which I thought would be nice to mention as well. Most of you probably know Enerchem. Enerchem is a Canadian company producing methanol and nowadays also ethanol, gasifying non-recyclable waste, so municipal solid waste, in a bubbling fluidized system. And they have announced several plants in Spain, in the Netherlands, but this one is the one on the number one on the agenda, and that's in Varennes in Canada, where they aim to build a standard Enerchem unit coupled to an 87 megawatt electric electrolyzer to supply hydrogen and oxygen for the system, which would not be feasible in Europe, they say, because the power prices in Europe are way too high, and in Canada, the electricity price is actually in average 4 to 5 times cheaper than in Europe. So making using electricity in Canada to produce hydrogen actually makes sense. And by doing this, they valorize much more of the carbon, so they won't have a CO2 outlet, but they aim to produce a maximum amount of methanol from this plant. And I think this is actually a nice example of where it could go to with regards to flexibility. Thank you.
Thank you very much, Berend. This does trigger some questions. You stressed that you need quite a lot of electricity if you fully want to utilize the potential, let's say the carbon potential in biomass. But well, if you compare it to, let's say, power to X solutions where you use direct air capture to get the CO2, then perhaps this might not be such a bad option.
It might not, because the CO2 is coming out of your process anyways. But my main concern at the moment would be, and I'm not a specific expert on producing electricity to go to hydrogen in the future. My topic is gasification, but if I look at the future sizes of these plants, and then if you look into the amount of electricity that would be needed as a base load to provide the hydrogen, that's quite a significant amount, and maybe it would work in certain cases, like in Canada, where there's already a lot of low cost electricity available, and it's much easier. But in the Netherlands, I think it would be quite a challenge to build an electrolyzer that size to valorize the excess CO2. And if you compare it to direct air capture, yeah, there you have also the energy consumption that you have on your direct air capture to obtain CO2. So in that respect, it's probably easier to use CO2 that's like a point source available from these gasifiers anyways. But my feeling would be more that it would go to a more decentralized, or that you have a plant operating to produce methane or methanol that the CO2 is shipped to a central location where you can actually utilize it in different ways, either power to X, but also other applications.
But so that is a topic then perhaps that might need more attention. So at what size should these type of plants be realized? So not only for gasification-based systems, but also for power to X systems based on, for instance, direct air capture.
Yeah, true.
Okay, but one other short question. So gasification really appears to be a very flexible technology because it's very flexible concerning the feedstock, but also on the product side. And then you also have these let's say sector coupling possibilities. Why is it not taking off to a larger extent? So what do you see as the
I think one of the main bottlenecks is that you have to go through a certain demonstration phase, which is if you compare it to a solar panel or to a wind turbine, it's a relatively small investment to de-risk your renewable energy system, the power panel, the solar panel or the turbine. If you go to a gasification-based system, you have to basically demonstrate it at a commercially or pre-commercial scale, which comes with an investment of several tens of millions of euros. And then that's one big step. And then the next step would be a commercial size plant, which would cost even more. So the investment needed to obtain a certain feeling of security for investors is significant, and until now there hasn't been, I think, a sound enough support system. And I think the EU and also in the Netherlands you see a shift that they realize that this is not taking off, but they identified the technology as important enough, so they are reconsidering, I think, how to invest in these technologies. If you compare it to the US, there you actually see very large demonstration plants up to 200 megawatts being built, and currently the fulcrum is I think in operation, or in the first startup should be round about now, and the second plant is the Red Rock biofuels is also built, so it's also roughly 200 megawatt large size, and there the investment is also made by the DOE partially, and it's a different approach, and yeah, hopefully it works there, because in the end we need this technology to be successful. Yeah.
Okay. Yeah. So let's hope it will really go in the right way in that sense.
Exactly. Yes.
Okay. Thank you very much, Berend, for this gasification perspective. Perhaps you can look at the Q&A for some additional questions. And then we go over to another set of technologies based on largely on digestion, so the biogas systems. And here an overview of the possibilities in terms of flexibility will be given by Jan Liebetrau. He's from Rytec in Germany. He's there the head of the department consulting and research, but he's also the task lead of task 37 of IEA Bioenergy on biogas. So he will give an overview of flexibility options there, and this presentation is entitled "The Integration of Biogas Systems into the Energy System." Jan, the floor is yours.
Thank you very much, for the introduction. I hope you can see and hear me clearly.
Yes, it's working fine.
And also my presentation, I assume.
Yes.
Yeah. Last but not least, we will discuss some issues around technical aspects of flexible plant operation. I would like to focus on the biogas application, which is factor 1,000 smaller than what we just have seen in the presentation before. So biogas plants tend to be much smaller than the plant size, what we just have heard. My name is Jan Liebetrau. I'm head of the Task 37. I'm task leader of Task 37. I would like to tell you a few things about Task 37, energy from biogas. We have 16 countries taking part in this task at the moment. And you can see here on this slide the topics we are dealing with within this triennium. And if you are interested, you're welcome to contact me. And also you can check on our website. We have all our products we produce there. There's also an interesting newsletter we publish every month. So feel free to get informed about biogas on our website. I would like to give first a short introduction on the context of flexibility within biogas systems, then highlight some technical aspects for the flexible plant operation, economics, give you some exemplars, and then last but not least, the conclusions. Biogas plants have a lot of options to operate flexible. Bernd has already mentioned a few. It starts with the substrate. It comes also on the utilization side. I will focus today here on electricity and heat production from biogas facilities. We have, when we talk about flexibility, the issue that we want to balance out a certain demand with a production which is right fitting to this demand. You can see here on the left side the black curve. This is on the AX market, the demand which is sold there. And the green curves, you can see the production of renewable energy in this market. And you already can see a lot of quite sharp peaks, which are responding to the peaks of the demand. And this is how renewable energy is already responding to the fluctuations of the demand. And a large share of this is already coming from biogas plants. This is the situation when you go into electricity market and electricity grid, but of course you also can be forced to handle a certain specific production on an industrial site. And on the right side, you can see the electricity demand of a dairy farm. And you also can see they're quite distinct peaks. And if you want to cover this electricity demand, then you have to align your electricity production as well. Whole different story we have when we come to heat demand. We have already seen that on the example of Vienna in the previous presentation. Heat, in particular, when it comes to the heat demand of housing, has a very distinctive seasonal pattern. And of course, this is a whole different story than the electricity. So if you have a CHP application and you have to serve these two masters, then you have to make sure that you have an operation which is able to answer to the demand on the electricity and also on the heat side. When you want to flexibilize your energy output from a biogas plant, then usually the standard answer would be to increase the installed CHP capacity and limit the hours of operation of the overall capacity. So that means you have a over capacity which you have to install. This results, of course, in a higher technical effort, higher CapEx, but also OpEx. And these additional costs, of course, they have to be balanced by the benefits of such a flexibilization. You might be forced to increase also the upstream capacity. So for instance, gas storage, or even the gas production rate of the process in order to balance out the changes in the gas demand when you convert the gas in limited hours per day, per month, however you decide. When talking about flexibilities, there are two different qualities conceivable. First of all, you could say, okay, I know that in the morning and in the evening, we have a peak in the electricity demand, and I will simply switch off and on and off my plant during the hours per day where most likely the demand is highest. And this would be the upper chart here, but a whole different story it would be if you answer directly to the very demand of the system. So then you need, of course, a prognosis, how the system will behave. And you need to translate this prognosis into a certain demand. And then you have to kind of combine this with the capability of your plant, and you need a model to calculate the answer of your plant. So these are two different stories which result in a completely different demand or requirements in regards of the control of your system. This is an example for a biogas plant, which is operated following the demand of the energy system. The green line is the fluctuation of the price at the ABEC spot. You want to respond to that because you want to have a high price value of your product. And the gray sections in this chart is the time when the CHPs are on. We have two CHPs here. The one is operated for most of the day, and the second one is only switched on during the high peak times over the day. And this is one option. You could have one CHP operating only for 12 hours. You could have one CHP operating only for 6 hours. This depends, of course, on your overcapacity, but just to visualize how such a flexible operation would look like. When it comes down to the technical questions, then of course a CHP which you might need to start and shut down once, twice a day, has of course some other technical challenges than a CHP which is operated 24/7. CHP producers have very quickly adjusted to these requirements, and here on this slide you can see some of the changes they have actually introduced to their systems. And nowadays CHP provider will give you a certain number of starts per day, what they think is good and the engine can handle. And other than that, a flexible operation when it comes to on-off operation is a very state-of-the-art operation. I just showed you a possibility for operation where two CHP engines have been installed on site. But the decision, if you go for several CHP units or if you decide for one CHP unit, has also an impact on the efficiency, overall efficiency of your plant. If you have a larger engine, then these larger engines, they tend to be more efficient than smaller engines. This is the first thing. Second thing is you can imagine to operate flexible by reducing the load, so moving into part load operation of a large engine, or you could do this by switching on off your engines. Part load operation has the big disadvantage that it significantly reduces your efficiency. So as you can see it in the table here, it goes down quite a lot, and it increases also your methane slippage. So you have also other increasing impact on the environment by operating in part load operation. So if you go for the decision, first of all, one large engine is more efficient than two smaller engines, and on-off operation is more efficient than part load operation. Moving upstream now from the CHP and looking at the gas storage, then the gas storage is being installed on every biogas plant to handle the deviation between gas production from the biological conversion process and the gas utilization. Standard is that they can handle few hours of CHP operation, and this gas storage capacity is usually limited. Now, if you want to go for a quite large overcapacity, then of course the balancing capacity which is needed is much larger than with a 24/7 operation. Then you might need some additional measures to improve your gas management. You could start with increasing the gas storage capacity. The precision of your sensors to go for filling level has to be increased. Transportation of the gas within the gas storage domes might be upgraded. Dimensions of the gas transportation lines might be upgraded. And also the dimensions of gas treatment. In particular, gas drying comes soon to its limits when it needs to handle all of the sudden twice the capacity as with 24/7 operation. Plus, what you also could do, gas management could also mean change the feeding of your biological process and change the gas production rate on your facility. This requires, of course, a little bit more sophisticated control, but it has already been shown that manipulation of the feeding rate gives very good results on the gas production rate, and you simply can control how much gas is produced when you need it. In general, when you want to have a really sophisticated overall control, you might also include variables like substrate costs. If I put additional substrate in, how much does it cost? Is this actually compensated, or is this coming back from the revenues I get from this additional input? Substrate characteristics as degradation rate, also meteorological data, which tell you the filling level of your gas storage, pressure in the gas storage. All these limitations, technical limitations of your plant, have to be fed into a control system which dynamically tells you how your system can answer to demand of your energy customer. Now I'd like to talk a little bit about the economics of this flexible operation. I've already said standard answer to flexible operation on the biogas plant is increasing the CHP capacity, and of course the CapEx for this is dominating the additional costs of such a measure. But of course there's also additional maintenance effort, and this overall package which you have to handle when you increase your capacity and you want to flexibilize your plant, this has to be paid back by the revenue. This is a calculation which has been done some years ago, and I don't want to go into the details here. I just would like to give you a order of magnitude what an additional CHP capacity of factor 2 would mean in additional costs on the power production. You can see on the second lowest row, power production costs. If we start with the left column, this is the reference case 500 kilowatt, we have production costs here of 18.7 cents a kilowatt hour. If you would double the CHP capacity to 1 megawatt, so twice the capacity installed there, this would mean an increase by roughly 2.5 cents of production costs for the electricity produced. So this 2.5 cents need to be compensated by an increased revenue from the electricity. And this can be achieved by producing, for instance, in a market selling the electricity to a market at a time where a higher price can be achieved. This is an example here, and this is an example from the good old times, I should say, in 2020. And you can see that the electricity price here was ranging on this day in January 2020 between some negative price up to 40 euro per megawatt hour. The revenue to be expected here in a 12-hour operation period of the CHP would be 1.5 cents per kilowatt hour. If we come back to nowadays, this has completely changed. As you can see in this slide here, this is the day-ahead auction and intraday market on the same spot market. And you can see that the prices have changed a lot. Not only the absolute numbers are far higher due to the high gas prices in Germany, also the fluctuation has increased a lot. So going into these peaks and producing only electricity in these peak times would mean a much higher revenue at the moment than it had been 2 years ago. I don't know how this will look like in 5 years or 10 years, but this is, I think, just to show that this can change a lot. And I think nobody knows how future prices will look like, but it highlights the need for flexibility on the energy provision. A couple of examples for flexible biogas plants. This is a plant which has been commissioned in 2010. They operate in a flexible way since 2019. They have almost five times installed capacity compared to their average output. They have a huge heat storage also to make a heat supply discoupled from the electricity production. And the CHP units there have, of course, only 1,800 hours a year full load operation. 5 times overcapacity is a lot, and this has been only possible to do this because this has been incentivized in Germany by the Renewable Energy Sources Act. Another important business case is the so-called virtual power plant. We have here an example of a Swiss virtual power plant. It's called Fleco-Power. And they had bundled a few years ago around 30 megawatts of power plants. What such a virtual power plant is doing is it's collecting, combining different energy suppliers and selling this bundle and the characteristics of this overall bundle to the energy market. And they can, of course, with this increasing capacity, have a whole different impact on the market than a single energy supplier. And there's also an example from Germany, which I just wanted to highlight because this shows, I think, quite the increasing relevance of these markets. They have started operation in 2009 when this virtual power plant has been founded. And they have now almost 15,000 units under contract, electricity producers. And they have a capacity over 11 gigawatts, what they already control and sell to the market. I think this is quite impressive number. It shows the relevance of these businesses at the moment and the increasing relevance for the future. To sum up, the perception of the role of biogas has changed. We have been talking in the past about treating organic waste, and energy supply has been increasingly important. But we are now talking about the flexibility of the supply because wind and solar have a impact on the energy system, which has to be somehow balanced out. Bioenergy can contribute to that. Bioenergy can provide energy at will, and biogas applications have shown that, I think, quite impressively. And to my understanding, this will be the future of biogas. And if you want to go into more details, then I can recommend a technical report, which has been published by the Task 37, which is also available on our website. I'm done with my presentation, and I thank you for your attention, and I'm happy to answer questions which have been coming up.
Thank you very much, Jan. It's always not the easiest task to be the last speaker in the role, but I think you did a very good job to give an overview of what's happening with respect to biogas systems. I think an interesting notion is that let's say this development from a biogas plant being a treatment plant for organic waste now developed into, let's say, a flexible units for energy production. I can imagine that that has also quite an impact for the owners of these plants. And you already mentioned the concept of virtual power plants. Could you shed some more light on that? I mean, if traditionally biogas plants were placed with farmers and are still placed in farmer communities. In terms of management and control, have there been considerable developments over the last years?
Yes, there have been considerable developments, that's for sure. And I mean, the whole story of the war in Ukraine has already changed that a lot, because we have, due to the increasing energy prices and the fluctuations, which I have shown in the presentation, of course, a lot of pressure on the market and a lot of interest also from the biogas operators to provide energy when it's most valuable. This has been enforced or supported by the government in Germany for quite a long time. And it's nowadays, it's actually an obligation that you have to have twice the capacity installed on the electrical output side compared to the average output of the plant. So plants are meant to be flexible, and with this situation at the moment, they are operating flexible. And the technical development we have seen there in the past was also that we have now these virtual power plants, and they actually, in some cases, they control directly the biogas facilities. So they remotely check upon the status of the operation, they check on the filling level of the gas domes, and then they operate these plants remotely, completely. There are, of course, different options for the plant operators, how far the plant operator wants to go. But we have these cases where plants are controlled remotely. Another option and another important point, I think, is also the heat. We have these plants, they are decentral. They have also a certain heat delivery, what they have to follow up, and it increases the overall efficiency. And it might also increase the revenue if plant operators are paid for the heat they deliver. And you can store some of the substrates for quite a long time. So they can decide, okay, I produce more electricity in winter, because then I can also make more revenue out of the heat. And we have seen these examples also in plant operation, beside the pure electricity market.
Okay, thank you very much, Jan. There are a few more specific questions in the Q&A, so perhaps you can have a look at those. I think this concludes the list of speakers. And I think with all these speakers, We've looked at flexibility provision from gaseous biogenic gases from multiple angles. I think we started out with the notion that flexibility, there are many options, many technical options, which was also recognized by the participants. Then we saw in the presentation of Helen that it's not only the bio-based flexibility options we need, but we need more than that, also when it comes to the utilization of hydrogen. So that even makes the energy system more complex, and we need that complexity to deal with intermittency options and to really have a versatile system. We saw from Vienna Energy that biomass gasification can play an important role, not only gasification of biomass, but also to see it as a option for to deal with various waste streams that do not have a higher added value application. And we saw from Siemens that on the technology side, quite a lot happens to make also to allow these various flexibility options. Then diving into gasification as well as biogas, we saw that gasification has a large potential, is now taking off, but still more has to happen there in terms of real investment in demo and first of a kind commercial plants. And when it comes to biogas, I think a lot is happening there. And especially in terms of management and control, these virtual power plants, these are really developments that further enable bio-based options to play their role in terms of flexibility. I think we should not dwell too long, let's say, and enter into a lengthy discussion. Also given the time, but what I would like to do is to ask the different speakers, let's say, to highlight one topic, one notion that was most striking for them in this workshop. So if you have, let's say, some thoughts, some topics mentioned this afternoon where you say, well, it's worthwhile to highlight that at the end of the workshop, then please go ahead. So may I give someone the floor to that feels to contribute in this sense in the end.
So maybe I will start then. For me, the most important point is that there are technologies in different maturities, and we will need all these technologies to achieve our goals. So it's important to develop all these approaches and make them available.
But do you feel that there should be, let's say, kind of a prioritization? Always the funding or the financial means are limited. So,
in my point of view, from the end user perspective, we need a broad base. So I think all technologies have their application. So it's quite hard to prioritize, because then you somehow reduce the flexibility in regard of the framework, for example, the markets. So in an ideal world, all technologies should be developed as fast as possible.
Okay, thank you. Any others? Tilman, I see your hand.
Yeah, I think that it's true what Teresa said. What I find striking is, Helen wants to be CO2 neutral in 8 years, and Vienna in 18 years, right? And most countries have signed a contract which says in 2050, which is 28 years. So that means any further investment which we do in principle should always already fit to that goal, because there's only one investment cycle. And that actually tells us that technology is one side, but my feeling is one of the issues is that the boundary conditions, and now I'm speaking about the regulations and which at the end translate into some economic boundary conditions, because at the moment we have regulations which somehow are not always balanced between all technologies, or sometimes you could even say some of them are not really fair. But there should be a clarity about these boundary conditions from the regulation side, because then the investments go in the right direction in the first try. Otherwise, we run the risk that people do not invest at all, because unless the regulations, boundary conditions are clear, they do not invest because they want to avoid the risk to invest into something which then they cannot use anymore.
Yeah, so clearly it's not only the technology side, but it's also non-technical issues like regulations, like incentives, and so forth that are of crucial importance. Any others? I see Hans Berend. Your hand was first, I think.
Yeah, I had two observations. I think the level at which certain technologies are, so the TRL or the commercially readiness level, is quite different, which makes the whole identifying the best pathway very difficult, very complex. So it's probably going to be a topic to be under investigation for the coming years, and it's good that Task 44 has taken up that glove to do that. And with respect of using hydrogen in a system, and that was more a personal realization making this presentation. If you look into the availability of surplus power in the future, I don't think it will be a lot. So I think there will be a scarcity of power supply in the future, meaning also renewable hydrogen. And then I think combining it in the Fischer-Tropsch process, making sustainable aviation fuel, there you need the least amount of hydrogen. So you can, with a small amount of electricity already, utilize more carbon. Plus, it's also one of the hardest to decarbonize sectors, and there's not a lot of pathways leading to SAF. So utilizing your precious green hydrogen in that pathway is probably, in my opinion, at this moment, probably the best approach.
Okay, thank you, Beer. This was not counter. There were no comments against this opinion in the chat and in the Q&A. So perhaps it has a broader support. Marcus.
Yeah, thank you. I just wanted to support that also. I mean, I don't know so much about the gasification technologies and so, but my impression is always that many of the technologies are already there. I mean, you talked a little bit that there are different levels of TRL in the technologies, but my impression is that many technologies are there, could be realized, but then it is a problem of regulation, of financing. So we are trying to find the business cases to make money out of it. But if we really want to, we could really change. So I'm sometimes a bit frustrated about that it's more discussion about money and so on, but the technology wise, we could do it. Just thanks.
Yeah, thanks. Any others who would like to highlight some thoughts or findings from the workshop? Yeah, Jan, please.
Yeah, I only can support what just have been said. I mean, we have seen that in Germany with the biogas sector. Once the support was there, we have seen a lot of development, and it was going up quite fast with the growth of the sector. However, the overall context, I think, was only the electricity. And so we have a lot of other sectors where not so much happened. And I think this is what we need. Oh, sorry. Yeah, there's some impatient child trying to get it. So there's a lot of development we have seen, but not in all the sectors. And I think what we need is a framework which puts a price on the CO2. And then, of course, we will have these different technologies sorting out where they fit in. And what was already said, we need them all. This is not the question, do we need this or that? We need them all. And we need a framework where they all can fit into an overall economy and related to the most efficient or the most cost-effective way they how convert energy into a product. We have I like the example of a German quota in the fuel system. And for advanced biofuel, we pay at the moment around 450 euro a ton CO2. This is a very specific market, but this is the only price at which a CO2 reduction can be achieved. And as long as we stay at 25 euros a ton, as the current price in Germany is, we will not actually reduce emissions in this sector. And that's what I think. We need an overall economy structure which allows the development of all these technologies and gives a long-term perspective to the industry to have a prognosis how they can develop into such an economy.
Well, thank you, Jan. I think this is a very clear appeal and also a nice conclusion for the workshop. I would like to thank all the speakers that contributed to the workshop. Also, of course, all the participants, of which many of them are still there, although we are after 5 and 5 o'clock is for many people the end of a working day. So that's a good sign. Thank you very much as well for the active participation in the Q&A and in the answering the Slido questions. And of course, thank you to Eta Florence for organizing and arranging this Zoom webinar. And with that, I would like to conclude the webinar and perhaps refer all the remaining participants to the IEA Bioenergy website, where the presentations will be shown in a few days, and where also you could look back at the webinar if desired. With that, I wish you a good evening and thank you very much.
Thank you. Bye.
Bye-bye.
Bye-bye.